I'd just like to start by saying thank you for inviting me to do this talk today. I am currently up in Durness in Scotland, with Wi-Fi connection doesn't seem to be great. So apologies if I glitch out a little bit or some of the animations are a little bit slow. But do bear with me and yeah, feel free to say if that is the case. So I've been invited to talk to you guys today at this amazing festival that's put on each year by the Scottish Geology Trust, about my PhD work. I'm coming into the final year of my PhD, and I've been spending most of my time trudging around the Garvellach Islands, and these islands, there's this chain of uninhabited islands off the west coast of Scotland, and there they are, shining in all their glory in the background of this slide. And the reason I come to talk to you today is that we believe these islands preserve a rare record of what's known as Snowball Earth. It's quite an enigmatic time in Earth history, and we believe on the Garvellachs we have a unique record of this time, which isn't present anywhere else on Earth. And before I start, I'd just like to acknowledge the person in the foreground there, and that man is Anthony Spencer, or Tony Spencer, and he did his PhD on these islands in the 60s and published an infamous memoir in 71 on these islands, and then some 60 years later, in the ripe old age of 84, Tony is still trudging around the islands with the A team of retired or soon to be retired geologists, looking to revamp his memoir with new observations and new thinking. But if it wasn't for Tony, I wouldn't be here today giving you this talk, and it's his invaluable insights and enthusiasm for these islands, which kind of has spurred on this research, which I'm going to show you today. So just a little bit of an idea of how the presentation is going to look. Hopefully the slide has moved on with the click of my mouse there. But I'm going to start with what is Snowball Earth. Some of you may not know what Snowball Earth is and may have just heard of it, so I'm going to give an overview of that. And then I'm going to talk about a problem we have in Snowball Earth science, and it's a problem which unfortunately can't easily be fixed in Earth history. But I'm going to move on to talk about then the unique geology of the Garvellach Islands and how I think that and we think as a team, the Garvellach Islands potentially do have the answer to this problem, which has kind of racked people's brains for years. And then I'm going to give you just a brief overview of some of the new research that I've recently published, and that's some new geochronological constraints for the rocks we have on the Garvellach Islands. And then I'm going to tie this all together in talking about what this means for geological time. So for those that don't know, Earth has three main climate states. And these took a little bit of time to pop up on our screen as we were practicing due to my lag, but hopefully you can see the greenhouse Earth there, our first climate state, and this is where we don't have ice on land or at the poles. And then we have the icehouse Earth, and that's the climate state that we're in today. And this is where we do have ice on land. We have ice at the poles. We're quite familiar with it because, you know, this is our modern day climate state. Now Earth flicks between these two climate states at regular intervals, and as Earth scientists, as geologists, we can somewhat predict at what rates these two transition between each other. It's reasonably cyclic, and these two climate states aren't that odd. Earth has a number of feedback mechanisms to ensure that Earth doesn't get too hot or too cold at any one time. So if an ice house is getting a little bit cold, it'll suddenly switch off one of its feedbacks or turn on one of its feedbacks and heat up, and vice versa with a greenhouse Earth, which is why we see the fluctuation between Earth's climate states through Earth history. Now, Earth's third climate state represents a breakdown of those feedback mechanisms and those Earth's natural thermostats, and that is the Snowball Earth. And the Snowball Earth is when ice covers nearly the entire planet, and that's kind of all the way from the poles down to the equator. And it's an incredibly rare climate state in Earth history. In fact, we have to go some 635 million years back in Earth history to when we last had a Snowball Earth climate state. Now, we're going to be looking at the Neoproterozoic era here in this talk, and some of you may be familiar with this era, particularly the Ediacaran, as the first animals emerge. But it's really kind of pivotal time in Earth history. Before the Neoproterozoic, the atmosphere is kind of nothing like what we have today. We don't have modern levels of oxygen. And kind of perhaps more interestingly, the fossil record is pretty sparse. We don't have complex life. We don't have multicellularity in the forms that we know it today, i.e. animals. And slap bang in the middle of the Neoproterozoic is the Cryogenian. And in the Cryogenian, there's two of these Snowball Earth events, if you like. We have one potentially further one in the Ediacaran, but we'll ignore that for now, as that's a little bit more contentious than the ones we have in the Cryogenian. So these two Snowball Earth phases are potentially the only times in which we have a definitive Snowball Earth climate state in Earth history, and that's what I will be focusing on today. Now, these two Snowball Earth glaciations that make up the Cryogenian are made up of the Sturtian, which is the older of the two, and that lasts from between kind of 717 million years ago to around 658 million years ago. We have a small period of interglacial period of non-glacial, and then we have the Marinoan, which is a far shorter glaciation, lasting from between 650 to 640 to 635 million years ago. And the Sturtian, it's the first thing that's apparent is the sheer length of time of the Sturtian glaciation. I'll say it's a 60 million year glaciation almost. Now, that's nearly the length of time between us and the dinosaurs. So it's quite hard to wrap your head around for that length of time and what that would have done to the planet. So again, I'll just step backwards and we'll talk a little bit about this history of the Snowball Earth hypothesis, as I think that's important to see what can get us to where we are today and what more needs to be done, and what unanswered questions we have in the world of Snowball Earth, and what I've been trying to tackle with my PhD. So it was right back in the 1930s when people started recognizing that we had a global distribution of Precambrian glacial deposits. So Precambrian being anything before the Cambrian period, we're around anything before 540 million years ago. And we now know today that Snowball Earth deposits cover all 5 continents and have a vast global distribution. I fear this is when my presentation might lag because there's a few animations, so apologies if so. Now fast forward to the early 70s, and this is when Tony, who's nicely positioned just below there in the photo in the background, he publishes his memoir on the late Precambrian glaciation in Scotland, and his evidence was mainly based on observations he saw on the Garvellach Islands and on Islay. And what's amazing about this quite classic piece of geological literature is that it still holds true today. A lot of the observations that Tony made, you can walk on those islands and see today, and it's quite remarkable how some 50 years later, this stands the test of time. And I think that's an important thing to note in what we're going to talk about throughout this talk. But it wasn't until the early 90s, we knew we had these widespread global glacial deposits. However, we didn't have a true handle on what plate tectonics was back in the 30s. But by the 90s we did, and we had people doing paleo magnetism studies, so where continents may have been in the past. And it was these studies that kind of pointed towards the fact that glaciation might have been occurring at the equator. And this was a real kind of head scratcher for a lot of people at the time, because frankly, that shouldn't happen. Now, Joe Kirschvink here in the early 90s, he was trying to disprove the data which suggested that glaciation occurred at the equator at the time in the Precambrian, but the evidence was insurmountable, and he actually ended up coining the term Snowball Earth. However, unfortunately for Joe Kirschvink, he did so in a 7-paragraph long paper, hidden within a kind of 1,300-page book. So it wasn't until the late 90s when a man called Paul Hoffman came along and the snowball hypothesis grew legs. It really started to gain traction. Hopefully you can see a picture of Paul there. He's standing on the right, and his PhD student, I think it's his PhD student at the time, Dan Schrag, is on the left. And they're pointing at what's known as a cap carbonate in Namibia. And Paul took all the evidence that they have before them, and the ideas of Joe Kirschvink, and basically came up with and kind of expanded the Snowball Earth hypothesis. And they now had a model whereby glaciation in the Precambrian must have occurred very, very quickly if we had ice at the equator. A process known as runaway albedo would have occurred, which is whereby ice that descends below 30 degrees latitude is cooling the planet via reflection of sunlight at such a great extent that it overrules all of Earth's feedback loops, which prevent it from getting too cold, and Earth then descends into a snowball Earth. That was kind of the ideas of Joe Kirschvink. And then Paul Hoffman built on that, and he came up with this idea that deglaciation would have been equally as rapid. And he's pointing there at what's known as a cap carbonate. Now, deglaciation would have occurred as, the Earth wouldn't have been stagnant during a snowball Earth. We would have still had volcanic eruptions, and CO2 would have still been building in the atmosphere. And it would have built to such a critical threshold that Earth would have got so hot that deglaciation would have also been rapid. And we would have had massive amounts of CO2 in the air. We would have had a period of intense warming. And because of that, we would have had the deposition of what's known as cap carbonates, which he's pointing to there. So the Snowball Earth hypothesis was really gaining traction. And it's kind of thanks to Paul that people have kind of built their careers on studying Snowball Earth. Now, a lot of these Snowball Earth deposits weren't dated, and we didn't have an idea of how old they were. And it wasn't until 2010 when one of Paul's PhD students came along, Francis McDonald, and they got some age constraints on a few of these Snowball Earth deposits. And true to the Snowball Earth model, they found that glaciation occurred synchronously round the Earth. And similarly, deglaciation occurred synchronously around the Earth. So we now have this idea that there was a widespread glaciation. There was glaciation at the equator. It must have been global, because we must have had this such strong albedo effect, this reflection of the sunlight, formation of these carbonates above glaciation. And we know now, due to geochronology, that it happened quite synchronously. Now, the next thing that I've included is something from my PhD supervisor, Graham Shields, who was the chair of the Cryogenian subcommission in kind of the early 2010s. Now, what they did is they decided to move the basal Cryogenian period based on the new geochronological constraints. They moved it from 850 to 720 million years ago, and this was quite significant, as this kind of provided a new constraint, a new bracketing for the Cryogenian period. And the Cryogenian period now brackets the concept of the Cryogenian period, which is these Snowball Earth glaciations. And they say in that 2016 paper that the boundary for the basal Cryogenian has been moved to 720 until a GSSP is found. Now, one of the questions that I've been trying to get at and understand, and kind of one of the main unanswered questions we have in Snowball Earth science is how and why Earth descended into this strange climate state. I've already mentioned that this shouldn't really happen. It's quite a rare thing to occur. It hasn't happened. It didn't happen kind of in 3 billion years of Earth history, and then it hasn't happened since the Snowball Earth in the Cryogenian. So we want to understand why Earth's thermostat broke not once but twice during the Cryogenian. However, we have a problem, and anyone that's been to a modern glaciated environment, take the Alps, for example, or even look a little bit more locally, like Scotland or the Lake District, and you can just see the incredible erosive power of glaciers. They pretty much plow through everything in sight. Modern glacial erosion rates are up to 100 millimeters a year. And we see that in the rock record. These are two pictures, hopefully that you can see of Snowball Earth deposits, and they're made up of clasts, angular clasts that have clearly been ripped up from beneath a glacier and transported an unknown distance and then emplaced on the land. On the right here is an infamous outcrop cliff face on the Garvellach Islands, and what that is it's a carbonate raft which is about 40 meters in height and about 100 meters wide. You can't quite see the full extent of it. You have to go around on the boat, but that is a chunk of carbonate that's been ripped up by a glacier, transported some distance, and then it's been folded here by the sheer power of glaciation. So they're incredibly powerful things, incredibly erosive agents. So what that means for geological time is that if we want to get some of those questions of how and why Earth descended into the Snowball Earth, we need the rocks. However, we have this massive issue, and it's a bit of what we call an unconformity problem. We have a missing time gap in Earth history between the late Tonian and the Cryogenian, and that's because the glaciation and the power of the glaciation associated with the Cryogenian Snowball Earth has removed much of that late Tonian record. And as we kind of come to understand the rock record around this time more and more, we find that we just get more and more disappointed in the fact that we understand now that up to 20-30 million years of Earth history in some locations around the world in the late Tonian have been pretty much removed from the record. So it becomes really difficult for geologists and scientists alike to try and get at some of those questions, because we simply don't have the rocks to test our models and hypotheses on. However, I'm hopefully going to take you on a small field trip now to the Garvellach Islands and try and show you that that potentially on these chain of uninhabited islands off the west coast of Scotland, the Dalradian supergroup, which some of you may be familiar with. It's this supergroup which spans across Scotland and Ireland, and it's bound by the Highland Boundary Fault to the south and the Great Glen Fault to the north, and it was deposited between the Tonian and Ordovician times, so around 840 to 480 million years ago. But I'm going to kind of hopefully show you that these age constraints were a little bit loose, and we're working on improving them. It's made up of 5 groups, which I won't in the interest of time go into. But the Garvellachs are just there in that star, because I fear that some of my kind of images and things might not have worked in the previously. So just slide. So now can you see a geological map of the Garvellachs? Perfect. So zooming in on the Garvellachs and looking at that geologically, this is a Garvellachs oriented in its kind of normal northwards position that you'd see on a map. But I'm going to kind of spin it round and just zoom in on it there. And now what we can see is it younging upwards. Sorry, yes, from kind of south west to northeast, and it's a chain of uninhabited islands that we'll start with kind of Dunconnell on the left there, the smallest of the islands. Then we move to Garvellachs in the middle there, which is the largest of the islands. Then we have Hooley, and then we have Aileach an Naoimh. And Aileach an Naoimh has kind of some more recent history, which people maybe may know of and may find interesting, but it has these beehive huts on, which can be dated to the 2nd century, which are quite amazing to have kind of this amazing historical story from 700 million years ago or so, but also this amazing kind of recent historical story on these uninhabited islands. But I focus on Garvellachs, the large island, and it's in this red box you see here that I mainly spend my field seasons poking around in. And this is where the transition is, if you like, from those late Tonian rocks into the Snowball Earth deposit of the Porter-Skeg Formation. Now, the Porter-Skeg Formation, it sits within the middle of the Dalradian supergroup, which is the log on the left there. It's 1.1 kilometers thick, so it's quite a thick deposit. It's made up of 5 members. And these have been divided into 48 discrete diamictites, which look something like that. Hopefully you can see that on the screen. Between these diamictites, we have some sandstones, and we also have some minor siltstones and dollarstones in the Porter-Skeg Formation as well. Now, the Porter-Skeg Formation outcrops throughout the whole Dalradian. However, the most famous and the best exposed and the most complete sections are found on the Garvellachs and on the Isle of Islay. On the Garvellachs, we have members 1 to 3 of the Porter-Skeg Formation, but we also have this preserved carbonate platform below, which is called the Garvellachs Formation. And this is what I'm going to kind of focus on now, as this is where I believe makes the Garvellachs so unique geologically speaking. So the Garvellachs Formation, this is a drone image that's then been manipulated, so you're looking kind of along strike and down dip, and this is an arrow to orient yourself of where we're looking at in the stratigraphy. That's the kind of transition from the Garvellachs Formation into the Porter-Skeg Formation. Now, the Garvellachs Formation is roughly 75 meters of exposed carbonate stratigraphy. It's all dipping 30 degrees to the south, that's southeast, and it's beautifully exposed on these islands. You can really kind of walk along the coast there, and you really feel like you're kind of reading the rocks like a book, because it's got 100% exposure and it's tilted at that perfect 30 degrees that you kind of walk, and just field work is such a delight there. Next slide. So this is what the Garvellachs formation looks like. This has been logged at a kind of a very high resolution by Ian Fairchild, one of my the people that I work with, and has done a lot of work on these islands in the past. And then we can divide it up into three main facies. Three main depositional environments. If you're not familiar with facies, the term facies, and that they are a limestone facies, a limestone association, where the first kind of 37 meters is limestone, and we have these stromatolites there as well, which are microbial mats, life forms. And within the middle we have these siltstones, and then at the top we have some predominantly dolomitic lithologies. And this is where we start getting early signs of ice, or what we interpret to be early signs of ice within this carbonate platform. And this is where, along with the fact that we don't see a sedimentological break, we don't see an erosive contact, and we see a transition into the Portishead Formation, but it's these early signs of ice that really add weight to the fact that we might have a transitional section on the Garvellachs, and this is potentially unique globally. Now, I'll just point them out on the log here, because we won't return to this log, but we have scattered grains, which I'll show you some examples of in a second, and they're interpreted to have been potentially ice rafted. We have gypsum pseudomorphs, and we also have some erosion surface that again I'll show you why we interpret them to be potentially early signs of an ice house climate. And I'll just caveat what I'm going to talk about by putting this. Well, firstly, none of these things that I'm going to talk about alone would perhaps be interpreted as evidence for ice. And secondly, we've got to think about this contextually. We're moving into a glacial deposit, the Portishead Formation. So the fact that we interpret these to be evidence for early signs of ice is not that unusual, given the context of what we're transitioning into. So some nice pictures. All geologists like to see field photos. Now, this is the limestone association that I was talking about at the base of the Garvellachs Formation. And we have these stromatolites. These are microbial cyanobacterial mats, and they're some of the earliest life forms we have on Earth. And these are forming in limestone lithologies, calcium carbonates. And usually stromatolites, not always, but stromatolites like tropical environments. They like warm environments, and similarly does calcium carbonate. Calcium carbonate tends to precipitate in warmer climates. So Scotland at the time, I haven't got a nice map to show you, but at the time, paleo geographically, we're sat about 30 degrees south. So we're sat near the equator. So Scotland, during the times of early Garvellachs Formation deposition, was probably quite tropical, teeming, like shallow seas teeming with cyanobacterial life. Then we move up in the section. We get to around kind of 50 meters, 20 meters below the Portishead Formation, and we start seeing what we interpret to be these early signs of ice. We have what we think might be drop stones and ice rafted debris. Now, hopefully, you can see the arrows there that are now pointing at what we interpret to be potentially ice rafted debris. And these are two lithologies. We've got dolomite here, and we've got limestone. Now, limestone, the last occurrence of limestone below this bed was some 20 meters below in the stratigraphy. So something must be eroding down to limestone levels at a laterally equivalent section, and then depositing it here by some transport mechanism. Now, if we look at this picture again with the arrows to it, what's distinctive of drop stones is that you see it piercing laminae. You see it piercing the sedimentary record as things have obviously been dropped in from floating ice down into the sediment below. And you can kind of convince yourself if you squint here that might be happening to these dolomite clasts. We also have these granules, these rounded quartz grains, which when you get into thin section, this is when it gets really interesting because you start to see that piercing of laminae in thin section of these tiny quartz granules. And that's really cool because, you know, it's hard to conjure up another mechanism whereby granules would do that if they hadn't been dropped by some height. Bearing in mind we're looking at these rocks being deposited in shallow seawater, and quartz would definitely not would probably have come from the land. So it has to have been transported there somehow. We also have what we interpret to be periglacial emergence horizons. So where we have particularly on the right here, we have potential evidence of freeze-thaw, weathering and shattering, and we get this brecciation of the dolomite there. And then this has been kind of these cracks have been filled in with sand. And again, the mechanism there behind that might be this onset of icehouse conditions and this annual freezing and then thawing, causing this to occur. And this is just below the Portescue Formation, which is quite interesting. And then finally, we have gypsum pseudomorphs. Some of you may be aware of gypsum pseudomorphs as a mineral. It's a calcium sulfate. It's what's called an evaporite mineral. And people might be aware of these and more familiar with these occurring in hot, arid environments. Now, the key thing is actually the aridity, not the hot parts as such. Now, the most arid place on Earth today is Antarctica, and actually, when you have ice forming on land, that's drawing a large amount of water out of the sea, leaving behind these brines, which become hypersaline and then precipitate minerals such as gypsum, and we find these today in glaciers and on bays actually in Antarctica. So we can be reasonably confident that in this instance, potentially that's another early sign of ice. And all this occurs just before we get to the definitive glaciation, which is the Portescue Formation. We start to see clasts of dolomite, which have clearly been ripped up from a laterally equivalent section and transported and brought there into this diamictite. Tony has placed these rocks here on what he sees as the boundary between the Garvellachs Formation and the Portescue Formation, but it's quite hard to define because it is so transitional. These clasts just start appearing and then they get in higher abundance, and the transitional nature of it almost makes it difficult to define when one formation finishes and the next begins. So I've hopefully shown you that we have this quite amazing record of glaciation and descent into glaciation on the Garvellachs, and that tiny kind of 70-meter section. But we have an issue with making this significant, and that is we don't know the age of the Portescue Formation. As I told you earlier in the presentation, hopefully if it wasn't glitching out too much, we have these two Snowball Earth glaciations. We have the Sturtian glaciation, which is the longer of the two, and then we have the Maranoan. And there's been an ongoing argument as to where the Portescue Formation fits within the cryogeny, which one of them it is. And that basically comes from the fact that we only have one glacial deposit in Scotland. So it could be if it is the Sturtian, then we're missing the Maranoan deposit, and if it is the Maranoan, then we're missing the Sturtian deposit. Let's just say. So what do we have geochronologically constraining the Dalradian? Well, we have an age for the basement rocks, so it must be younger than 806 million years, and then the next geochronological constraint we have doesn't occur until the top of the Dalradian there, which is 601 million years, let's say. So we have 300 million years of Earth history, where we're kind of scratching our head as to where things fit. And this isn't for geology, but it's very strange for people that aren't familiar with geology, that geologists walk around these rocks with a 300 million year time window to work in. And within the middle of that, we have the Portescue Formation. It's worth noting that 300 million years of Earth history encompasses the whole Cryogenian period, both of those Snowball Earth glaciations. Now, we've had an idea for a long time, and people before me have worked extensively on this, that the Portishead Formation represents that older, longer Sturtian glaciation. We have, if we look across to our Irish friends and the Dalradian in Ireland, we do have a framework of 3 glacial episodes there that obviously haven't been preserved to the same extent in Scotland, of which the Portishead Formation is the oldest, which, that they call it the glacial trinity, which would be Sturtian, Marinoan, and then the younger Ediacaran glaciation. So we have a stratigraphic framework in the Dalradian, which does seem to indicate that the Portishead Formation is Sturtian. We also use isotopic means to constrain ages when we don't know the age of the rocks that we're looking at in particular, and we correlate from other global sections. And the carbon and strontium isotopes, which I won't go into in great detail, seem to also imply that the rocks below the Portishead Formation, i.e. the Garvellachs Formation, are late Tonian rocks. And this is perhaps one of the stronger bits of evidence we have, because the strontium isotope composition of the seawater before Marinoan rocks, before the Marinoan glaciation, is a lot higher. It's a lot different to what we see in the Garvellachs Formation. Additionally, we have iron formations in the Portishead Formation, which are only known from Sturtian deposits. And we also have molar tooth structure, which is a carbonate fabric texture, which is only known from pre-cryogenian sediments. So there are 2 other pieces of evidence. However, we still don't have a direct age constraint, and therefore, I mean, even just last year, a paper came out with some age constraints from within the Dalradian using rhenium osmium. Whether you believe them or not, they then use them to suggest that the Portishead Formation was Marinoan. So this is really, people are sitting on both sides of the fence here. So I wanted to try and get at this question. I wanted to try and add some geochronological constraints. Those people that might not be aware of how difficult that is for a sedimentary succession, we don't have any ash beds which can be directly dated. We don't have any fossils which can be biostratigraphically constrained. So what I did is I collect sandstones, and sandstones contain this mineral zircon. And zircon is an amazing mineral for geochronologists. It forms in magma chambers, and when it forms, it incorporates uranium, but doesn't incorporate lead. And from that point, it's like a little ticking timer, because uranium decays to lead over time at a known and steady rate. And we can use this rate, and we can measure the uranium isotope composition of these zircons to constrain an age for them. Now, naturally, a sandstone is made up of lots of different sediment from wide variety of sources across the ancient continents. So we get ages all the way in these sandstones, all the way from the Archean through to the Cryogenian. But sometimes, fortuitously, you do happen upon zircons which can constrain what we call maximum depositional ages. So they constrain that rock cannot be older than that zircon that you find within the rock. And that is exactly what happened when I analysed these samples. I purposely analysed a lot of zircons per sample, so that the chances of falling upon some of these young zircons was greater, but I didn't quite expect the results to be this good. We had 8 samples out of the 11 which yielded zircons which fell within the constraints of the Sturtium. So if we look here, we have the stratigraphy of the Portishead Formation on the y-axis there, and then we have the samples that have young ages which are meaningful to us, and we have age on the x-axis. And we had 8 samples which yielded zircons which fell within the constraints of the Sturtian glaciation. 2 samples below the Portishead Formation, and neither of them yielded zircons which were younger than the onset of glaciation. That's good. That's a good thing. We didn't want that. And similarly, the uppermost sample here, which was taken from just after the final diamictite in the Portishead Formation, and this is what was so remarkable about this, we got an age of 662 from the youngest zircon there. Now, this is in strong agreement with other global locations, which suggest that deglaciation occurred around 660 million years ago. So I couldn't quite believe it when we got that age, but and similarly, the zircons within the Portishead Formation have this younging uptrend, which is suggestive of zircons which are close to depositional age. So all of this seems to point at having a Sturtian deposit. Now we finally have some geochronological constraints for the Dalradian within that massive 300 million year time span, but two, more importantly for me, the Portishead Formation now has some age constraints. Now, if we combine these new age constraints and as well as the indirect evidence that this is a Sturtian deposit, with that evidence that we have this transitional section, we perhaps have the most complete record of Sturtian glaciation known on Earth. And I think that's quite cool. On these uninhabited islands off the coast of Scotland, which you wouldn't visit otherwise, they have this remarkable record, which appears to be unique globally. So what do we have? We know we have rocks defining the Tonian cryogenian boundary, where we have the Garvellachs Formation on one side and we have the Portishead Formation on the other side. Now, this went a little bit crazy in the news. I don't know whether anyone saw it, but I published this article and it got blown, I'm not going to say out of proportion, but it got picked up by the news and people seemed to find it interesting. And I was happy to see the Garvellachs in the news. The BBC ran a piece on it. And I love this headline here: Ireland and Scotland still have rocks which carry rare evidence of Snowball Earth, as though it's a kind of, I don't know, coin collection that someone's got at the back of their wardrobe and they've not been telling people about. And it even got me some airtime on BBC World News, which was an amazing experience. And I enjoy talking about these rocks, so why not? But what this actually means and what the significance of this is what I'm going to talk about now for the last few minutes. I'm sorry I'm overrunning, but that's probably the technical difficulty. So I hope that's not a massive issue. But in geology, we divide geological time by events. It's people might not know this, that don't know the science of geology, but we don't use absolute ages, because as you've seen from the Dalradian, that's impossible for large portions of the geological time scale. What we use events which are based on concepts which we've come up with as geologists and earth scientists. And at the base of each geological period that we've dissected Earth history into, we place what's known as a GSSP, or a global strata type section and point, informally termed a golden spike. And these are a rock-based division of geological time, and it allows for global correlation for the starts of new geological periods. So they're really important things. There's only 12 currently on Earth for geological periods, and the cryogenian's next in line, the basal cryogenian's next in line. Here's a picture of the Ediacaran GSSP, which is in Australia, in one of those cap carbonates that Paul Hoffman was pointing at the start of the presentation. And what GSSP means, and what we have to argue for, is that this is the best geological example of what we consider it to mean to change from one geological period to the next. However, up until now, the unconformity issue has stunted efforts to define the basal cryogenian. That issue of that missing late Tonian record has meant that we can't really place a GSSP at kind of a time gap. So these are some requirements that have been laid out by Graham Shields when he was this chair of the subcommission. These are the things that we should be searching for as people who study this interval of time and are seeking out defining the GSSP. And I want to just point out continuous sedimentation across the contact there. And that's probably, these aren't in any particular order, but I think most people who study this and most geologists would agree, if you get to that one and you can't say yes, you're in a little bit of trouble. So these are late Tonian sections from around the world, and just based on that criteria alone, we can cross off all of them. which leaves us with two potentially transitional sections, the Garvellachs Formation in Scotland and the Tamiang group in Ethiopia. Now, unfortunately, another one of the criteria is that it's got to be accessible, and it's got to be a place which people can visit for both scientific and tourism reasons. And unfortunately, this locality is in northern Namibia, which is in a kind of a difficult place politically, and the evidence for this being a transitional section has only been really put forward by a handful of papers. You know, we can't really test what they're trying to say, and that's unfortunate. It's something I hope to be resolved in the future, but we really are only working with the Garvellachs Formation in southwest Scotland. So, is the basal cryogenian inbound? Well, we have the Cryogenian Subcommission working at this, and this is a subgroup of the International Commission of Stratigraphy. They have 21 voting members from all around the world, and they've visited Garvellachs Islands about 3 or 4 times now. This is me with them in 2022, and this is me with them earlier this year. I think I was taking a photo there. And we had a conference just before this visit, and we decided that kind of or the subcommission decided, let's say, that candidates will be put forward in spring 2025, and members will then vote in the summer of 2025. And I'm pleased to say that Garvellachs Islands are the leading candidate in that kind of race for the cryogenian GSSP. So I'm just going to leave you with my favorite headline from the news, which was "Golden Spike discovered in rock formation reveals when Earth became a snowball." And hopefully just from my short talk, you can see why I find that a little bit funny. The next kind of unfortunate / funny thing from the news was the fact that they chose to choose a picture of me hammering a carrot into the rock face as their main image. So probably the most prolific moment in my academic career so far has me looking a little bit confused, holding a carrot, hammering it into a rock. So just as I'm trying to convince my family that geology is a real science, this pops up, you know. So yeah, thanks very much, BBC. That was supposed to be a joke that stayed between me and the field group that I was with at the time. And I'd just like to quickly just acknowledge a few people before I finish. As I mentioned at the start, Tony Spencer has been working on these islands, you know, sandwiched in kind of in between he's had a full career in the oil industry, and he's come back to these in his retirement, and he's championing an A team of people who trudge around these islands. And it's inspirational that a man in his 80s is still doing this, and he's the most humble man I've known in academia, and he would hate the fact that his picture is being plastered on this. Likewise, Ian Fairchild is working on this memoir, and he is actually the person that kind of made a lot of these first observations of the Garvellachs formation. So we owe the credit to him there. And then finally, my supervisor, Graham Shields, is the person that first kind of suggested that I go and join Tony and trudge him around these islands. So just again, that's the end of my talk. If people found this slightly interesting, my supervisor has brought out a book just last year called Born of Ice and Fire, which is a lot more jazzy than what I spoke about, and it's very inaccessible. So if people are interested in learning about Snowball Earth a little bit more, then that's a good place to start. So yeah, thanks very much, and I'm happy to take any questions.
Brilliant. Thank you very much for a fantastic talk. Lots of thank yous in the chat. Everyone's saying it was a really interesting talk too. Somebody made a comment that it was a shame that you've just missed the 5th edition of Geology of Scotland.
Yeah, no, I know it was it was a bit of a shame, and the Tony Prave who wrote the chapter on the Dalradian, he did make a few jokes that the data would have looked nice in that chapter.
So Roger's asking about.
Sorry about the technical issues at the start.
Oh no, that's okay. These things happen. If you have a question about the cause of the snowball effect, what do you think is the kind of leading cause?
Yeah, I mean, it's a great question, and that's actually this whole project and these detrital zircons were very much a side project in my PhD. And yeah, people always talk about side projects during their PhD, but my main project is actually to try and understand how and why we found ourselves in a snowball Earth 720 million years ago. Now, the leading theory is known as the fire and ice hypothesis, which is aptly termed Born of Ice and Fire, Graham's book there. So, shameless plug for him. Read his book if you want to know more. But just briefly, at the time, the Earth's continents were clustered around the equator in a supercontinent known as Rodinia. And just a couple of million years before the Snowball Earth glaciation, we had the emplacement of a really large igneous province called the Franklin Large Igneous Province across Laurentia, which is what modern day North America is. And people believe that this emplacement of the large igneous province would have basically provided Earth with a lot of fresh, heavily weatherable material. And what happens when you weather mafic rocks in particular, they have cations like calcium and magnesium, which are readily react with carbon dioxide in the atmosphere during chemical weathering. So that would have drawn down large amounts of carbon dioxide. Similarly, that Franklin lip and that fresh rock would have also been weathered into the oceans, providing lots of nutrients to the oceans. And then you get ocean margins, which are then full of life. We know that life, primary productivity, likes to draw down CO2. We would have had an amount of carbon burial during the descent into the cryogenium. So these two things would have been cooling the planet. But as I mentioned, it's not the only time in Earth history where a large igneous province has erupted. People might be familiar with the Deccan traps, the Siberian traps, and we haven't had a snowball then. However, it's the perfect storm. It's this eruption of this large igneous province whilst the continents are around the equator, and I'll just kind of unpack that a little bit. But as it means that as ice is forming at the poles and descending down to lower and lower latitudes, that silicate weathering thermostat, which otherwise would have been shut off. So the reaction between minerals and carbon dioxide, which draws down CO2. If the continents were at higher latitudes, ice blocks that reaction. So that means the silicate weathering thermostat would have been shut off. So then given chance for CO2 to rise, we go back to nice conditions. The fact that the continents were around the equator means that ice couldn't encroach far enough down and cover enough of the continents to turn off that silicate weathering thermostat. So it was continually going and going and going and drawing down more and more CO2 until we get to 30 degrees latitude, which is when we have a process known as runaway albedo, which hopefully I didn't butcher in the kind of introduction, which is where we have kind of so much reflection. We have so much ice covering the land that the reflection of sunlight cools the planet to such an extent that it overrules Earth's usual feedback mechanisms. So it's this perfect storm of Franklin lip, fire and ice combined with the paleogeography of the planet at the time.
Fantastic. Thank you very much. Yep, just more comments about really interesting talk. Thank you for the clear explanations. And one more question about the conditions and what they were like between the two Snowball Earth episodes. So what was the interglacial like?
Yeah, I mean, that's a really, really good question. Just as kind of Earth descended rapidly into glaciation, it also deglaciation we kind of predict to have happened relatively rapidly. During the Sturtian, CO2 would have been building up in the atmosphere to such an extent that it got so warm that it would have had to overrule that runaway albedo feedback. And the modeling suggests that would have been quite significant warming period. So immediately after the Snowball Earth, and particularly the Sturtian, that interglacial, you would have probably had a period of quite intense warming. And this is why we have this deposition of these carbonates just after the Snowball Earth, because they love kind of warm environments. And we would have had, similarly, glaciers grind everything up. We would have had a load of readily weatherable material, a load of what's called rock flour, it kind of scattered across the continents. And it doesn't take long for the rivers to suddenly wash that into the ocean, CO2 to react with that glacial rock flour, and potentially that's why we then descended into another snowball. But it certainly would have been quite a strange place to stand in the interglacial time. You would have had quite a flat landscape probably, or quite a strange landscape to look at. Yeah, hopefully that answered your question a little bit.
Yeah, thank you very much. I have a question about what's next for the proposal for the Golden Spike. Is there a local group that's putting together that proposal?
Yeah, so basically they have the subcommission, and the subcommission put out a kind of formal call to people in the community via the International Commission of Stratigraphy to basically say who has a proposal that for the Golden Spike. Now, I'm obviously part of a wide team headed up by Tony. Graham's my PhD supervisor, but I'll hopefully be part of that team that puts together the case for Scotland and for the Garvellach Islands. As you've hopefully seen, it's got quite a strong case, and we had this conference to discuss this, and it's very apparent that I'd be surprised if there was a lot of people throwing their towel into the ring kind of thing. I think Scotland is yeah, it's definitely the leading candidate, but we people may have things to say about that, and that's something that we'll have to tackle as we get to it. But yeah, it has to undergo due diligence, and there's a few processes before before it's decided. Hopefully by next year.